Welcome again. Today we will discuss tin and bismuth based reagents in organic synthesis. So, if you see the periodic table again, this was 3A, 4A, 5A, 6A. So, tin is here, tin is in the same group with carbon and bismuth is the same group with phosphorus, and they are post transition metals. And also they have diagonal relationship. So, we will see the chemistry of these two reagents today. So, first we will discuss tin based reagents in organic synthesis. First we will discuss synthesis of organoteins, tetraorganoteins, tri, di and monoorganoteins, organotin halides also. Then organotin hydrides, which are useful hydride reagents, and reactions of organoteins, still a reaction, that is the coupling reaction we will discuss, and reactions of tributyl tin hydride we will discuss. So, organotin compounds or stannins are chemical compounds based on tin with hydrocarbon substituents. These are called organotin compounds, and organotin plus 2 and plus 4 compounds are known since tin has two stable oxidation state, that is plus 2 and plus 4. However, organotin 2 compounds are not very stable and tends to polymerize rapidly. So, organotin 4 is the most stable and organotin 2 converts to organotin 4. The organotin compounds are also easily oxidized to organotin, which is more stable. Bis cyclopentadyl tin 2 is the only known stable organotin derivative. The tin atom of this organotin compound is sp2 hybridized. So, this is the structure with two of the hybrid orbitals involved in bonding with cyclopentadiene ligands. So, this is sp2 hybridized and two sp2 are engaged in this bonding and another sp2 accommodates this lone pair. So, this is the structure of this cyclopentadiene tin 2. And the four principal classes of organotin 4 compounds are mono, di, tri and tetraorganoteins, which are represented by Rn tin x 4 minus n, n is equal to 1 to 4, where R is any organic group and X is anionic residue like halide. So, first we will discuss synthesis of organotin compounds and tetraorganoteins. The first report is Grignard method, which is reported by Polish in 1885. So, tetraalkyls, tetraaryls, tetravinyls and tetraethyl tin compounds are prepared in quadratic solvents such as diethyl ether or tetrahydrofuran. Like here, tetrachlorotin is there with Grignard reagent and this compound is formed tetraalkyl tin, and you can see this R is coming here. So, 4 R groups has come and 4 molecule of MgCl2 is produced. Mixed tetraorganoteins may be prepared by reacting Grignard reagent with diorganotin halide or triorganotin halide. So, mixed also is possible by this method. So, what you have to start with this one, instead of SnCl4 you have to start with R dash 3 SnCl plus RMgCl 1 equivalent of Grignard, and this R comes to here and MgCl2 is the byproduct. So, R dash can be aryl alkyl or cycloalkyl. Varge method, the reaction of alkyl halide with alkali metals such as sodium. So, instead of Grignard you can directly use alkali halide, and that is the Varge method, such as sodium followed by the addition of stannic chloride also in the tetraorganotin. So, this is the equation, you can see SnCl4, 4RCl, 8 sodium in pentane, it produce tetraalkyl shield and 8 molecule of sodium chloride is produced. So, R is equal to alkyl or aryl. Some more methods are there, aluminum alkyl method also is there. So, organoaluminium compounds can be reacted with stannic chloride to produce tetraorganotin. The reactions are carried out in the absence of solvents. The addition of complexing agents such as ether is required for high efficiency. So, here ether is the solvent and this is the organoaluminium. So, this R then goes to the tin. So, you can see the tetraalkyl tin is produced and this R coming from the aluminium, and 4 equivalent of aluminum chloride is produced. Here also R will be alkyl aryl. Synthesis of tri, di and mono organoteins can be synthesized. So, the first organotene derivative which was isolated some 130 years ago was diethyltene diiodide by Frank Land. This organotene compound was synthesized by direct synthesis method that we will see. The direct synthesis may be carried out in the presence or absence of catalyst. So, the reaction of benzyl chloride with tin powder is one such example, and the toluene or water used as the solvent gave good yield of dibenzyl tin chloride. So, this is the dibenzyl tin chloride. Also, you can get tribenzyl also if you use 3 equivalent of benzyl chloride and 2 equivalent of tin, then this benzyl 3 SnCl plus SnCl2 will be produced. So, this will be actually I think Bn is equal to benzyl. And 3 equivalent of Bn 2 SnCl2 will produce 2 equivalent of Bn 3 SnCl plus 2 SnCl2. So, tri, di and mono organotenes can be produced by this method. Now, organotene halides, the organotene halides, particularly triorganotene halides R3SNX and diorganotene halides R2SNX2 can be easily converted to organotene hydroxide by base hydrolysis using sodium hydroxide or ammonium hydroxide. So, these are example. You can see this halides, if we treated with hydroxide, then the oxide or hydroxide are produced. Like hydroxide, you get this displacement reaction, X is displaced by hydroxide. Here also the oxide is formed here, 2 equivalent of X minus liberated, and when RSNX3 is used, then 3 equivalent of hydroxide generates this tin hydroperoxide plus 3X minus plus H2. Here also R can be alkyl or aryl. The trialkyl tin oxides are distillable liquids or low melting solids which are readily soluble in organic solvents. Diorganotene and monoorganotene oxides are polymeric solids, and exact structure for these oxides have not been determined due to their intractability. So, trialkyl tin oxide, this one is distillable liquid or low melting solid, but other one diorganotene and monoorganotene, these one are monoorganotene, they are polymeric solids, and exact structures for this oxide have not been determined. They are known to consist an extensive network of SN-OSN bonds. Now, we will see the hydride, the organotene hydrides. Organotene hydrides are generated by reduction of the mixed alkyl chlorides. For example, treatment of dibutyl tin dichloride with lithium aluminum hydride gives the dibutyl tin dihydride. So, you can see this is the colorless oil. So, this is the reaction dibutyl tin dichloride with half equivalent of lithium aluminum hydride will generate this dibutyl tin dihydride, and this is the byproduct. Now, this is very popular. We know that dibutyl tin hydride, but this is produced in a different method. This was produced by reduction of tributyl tin oxide with polymethyl hydroxyloxane. So, this is the equation, this is the hydroxyloxane and this is the tributyl tin oxide, and then this is produced byproduct, and this is the tributyl tin hydride. Also, this can be another equation. You can see oxide and this one NBU3SNH, this is the tributyl tin hydride is produced, and the hydride is a distillable liquid that is mildly sensitive to air, decomposing to the oxide, tributyl tin oxide. So, this is important that you have to store in a air free condition. So, if it is come in the air, then this hydride can be oxidized to oxide. Now, we will discuss reactions of organotene. So, first we will discuss Stille reaction. So, Stille reaction or the Migita-Kosugi-Stille coupling is a chemical reaction widely used in organic synthesis, which involves the coupling of an organotene compound with a variety of organic electrophiles via palladium catalyzed coupling reaction. So, this is palladium catalyzed reaction, as you can see here, and these are the reactants. So, a tin compound R1 will be actually the coupled, and these are the tin component, tin alkyl whole 3 plus R2X. So, R2 can be generally sp2 hybridized like aryl or alkynyl, but later we will see the allyls can also be used, allyl and alkynyls also. And this is the coupled product and this is the byproduct X SN alkyl whole 3. X are halides, chlorine, bromine, iodine, also pseudo halides OTF, OPOR whole 2. So, these are the X component. The R1 group attached to the trialkene tin is normally sp2 hybridized, as we have said earlier, including alkenes and aryl groups. However, conditions have been devised to incorporate both sp3 hybridized group such as allylic and benzylic substituents and sp hybridized alkynes. Organosterenes are stable to both air and moisture, and many of these reagents either are commercially available or can be synthesized. However, these tin reagents tend to be highly toxic. So, they are highly toxic, these tin reagents, so you have to handle carefully. X is typically a halide such as Cl, Br or I, yet pseudohalides such as triplets and sulfonates and phosphates can also be used. So, what is the mechanism? The mechanism of the Stille reaction is one of the most extensively studied pathway for coupling reactions. The basic catalytic cycle involves an oxidative addition of halide or pseudohalide to a palladium catalyst. So, this like other coupling reaction, this oxidative addition happens here, and this is the rate determining step. RDS, the oxidative addition will happen first, and this intermediate will form, and now the transmetallation of 3 with an organotin reagent will happen. So, this step is important. The R2 is coming from the tin, and this X will be displaced by R2, and XSN alkyl 3 is formed, and R2 adds to the palladium, and organotin reagent is formed, and reductive elimination of 5 to yield the coupled product. So, this we know in other coupling reaction also, this intermediate is formed, and after the reductive elimination the cross coupled product. So, this is the cross coupled product is formed, and this is the catalyst which is generated again. So, R1, R2, allyl, alkynyl, aryl, X is equal to chlorine, bromine, iodine, OTF, etc. L is equal to phosphyl ligand, alkyl is equal to methyl butyl. Now, examples. So, in general, the vinyl halides are common coupling partners in the Stille reaction, and reactions of this type are found in numerous natural product total synthesis. Normally, vinyl iodides and bromides are used. Vinyl chlorides are insufficiently reactive toward oxidative addition to palladium 0. Iodides are normally preferred. So, this is important. When you choose the vinyl halide, you have to choose either iodide or bromide, because vinyl chlorides are less reactive. Like here, if you see this enone with iodide and bromide is there, and with this tin reagent and palladium PPH3 whole to Cl2, the Stille reaction happens with only iodide, because here iodide is more reactive. So, this is important, and this CBr bond is untouched. So, Stille coupling happens, and these phenyls migrated to here. This is the review Stille reaction will be online 2004, and also the stereochemistry of the alkene is retained throughout the reaction except under harsh reaction conditions. A variety of alkenes may be used, and these include both alpha or beta halo, alpha beta unsaturated ketones, esters and sulfoxide. Vinyl triplets are also sometimes used. So, the stereochemistry is important. If you see this, vinyl iodide. So, this is vinyl iodide and this is vinyl tin reagent, and with this palladium catalyst PDPHCN whole to Cl2, and these are the other co-catalysts and additives, and then you get the Stille reaction. So, you see this double bond geometry, this is intact. So, you get this product. So, stereochemistry is retained. So, this is very important. The stereochemistry reaction will be retained. If you have a particular stereochemistry of the alkene, iodide or the tin, that the stereochemistry will be intact. This was published in Tetragon Letters. Some more example, acyl colloids are also used as coupling partners and can be used with a large range of organostannine, even alkyl tin reagents to produce ketones. So, this is an efficient method to generate ketones from acid chloride. You can see this is the acid chloride, and this is the tin compound with the furan motif is there, also aldehyde motif is there, and when you mix them with this catalyst and HMPA toluene heat, you get this product. This is the ketone. You can see this is the ketone component which is generated, ketone component. So, ketone component is coming from the acid chloride. So, SnBu3 is displaced by this group. This was published in Finland 1993. Also, allylic, benzylic and propargylic halides can also be coupled, while commonly employed allylic halides proceed via eta 3 transition state, allowing for coupling with the organostannine at either the alpha or gamma position, occurring predominantly at the least substituted carbon. So, if you see, this is the allyl bromide, this is methyl, allyl bromide, and this is the vinyl tin reagent. And when you mix them with palladium, first this pi allyl palladium will form, pi allyl palladium. These are important intermediates in palladium chemistry. Pi allyl palladium will form because this is allylic bromide, and then the Stille reaction will happen. So, this is the Stille reaction, and this is very important, the least substituted carbon. So, the Stille reaction will happen at the least substituted carbon. You can see this carbon is substituted, but this one is unsubstituted. So, here the reaction will happen and the olefin geometry will be retained. So, this was published in JACS 1984. Now, we will see some examples of the Stille reaction in natural product synthesis, because Stille reaction is a powerful cross coupling reaction and has been applied in many natural product synthesis. So, Overman's 19-step enantioselective total synthesis of quadrigemine C involves a double Stille cross metathesis reaction. The complex organostannine is coupled into two aryl iodide groups. After a double hex cyclization, the product is achieved. Like this one, you can see two iodide motifs is present here, and this is the tin attached to the double bond. So, what happens, this R1 is this, the Stille reaction happens with this catalyst, and these are ligand co-catalyst, and after 3 steps you can get this natural product. So, these are some processes there. After double hex cyclization, the product will be formed, and this was published in JACS 2002. Also, Panek group reported a 30-step enantioselective total synthesis of ansamycin antibiotic mycotrinol, makes use of a tandem Stille type macrocycle coupling. Here the organostannine has two terminal tributyl tin groups attached to an alkenes. So, organostannine, you can see this is the structure of organostannine, two terminal tributyl tin groups are present here. And this organostannine reaches two ends of the linear starting material. So, this is the linear starting material, and here two vinyl iodide group are present. So, iodide here, and you get this product. So, this is the trans geometry is retained because vinyl iodides are trans, and with this after some CAN oxidation and HF, that is the TBS group, TIPS group deprotection, you get this natural product microtrienol. So, this is very important that two CC bonds are forming. In a single reaction, because two tin components are there, so two CC bonds are forming. This was published in JACS 1998. Some more variations are there, style carbonylative cross coupling. So, we have seen the synthesis of ketones from acid chloride. Now, we will see the synthesis of ketone with carbon monoxide. A common alternation to the style coupling is the incorporation of a carbonyl group between R1 and R2, serving as an efficient method to form ketones. The style carbonylative cross coupling employs the same conditions as the style coupling, except with an atmosphere of carbon monoxide being used. So, the carbonyl group is coming from the carbon monoxide here, and the carbon monoxide can coordinate to the palladium catalyst after initial oxidative addition. So, this is the mechanism actually. So, oxidative addition will happen as usual, and now at this stage the carbon monoxide will add. So, carbon monoxide is adding to the oxidative addition complex, and here also another oxidative addition, followed by carbon monoxide insertion into the palladium R bond. So, this will complex will form, and then the insertion will happen. So, this is the insertion, this is a very important step. Carbon monoxide inserts between palladium and R1, and after that transmetallation will happen with this tin compound. So, X will be displaced by that R2, and this intermediate will form where palladium is attached to R2 and CO R1. So, this is the main intermediate here, and after reductive elimination you get this ketone, and the catalyst ligand is regenerated. The transmetallation step is normally the rate determining step. So, here this is the rate determining step, transmetallation step. So, you can see palladium R is formed here, this resulting in subsequent reductive elimination to the ketone. And R1 R2 is allyl, alkenyl, aryl, S is equal to Cl Bri, O triplet, L is equal to phosphine, alkyl is equal to methyl butyl. So, still a carbonylative cross coupling. Now, we will see some examples. Larry Overman and Quackus made use of the style carbonylative cross coupling in their 20-step enantioselective total synthesis of strychnine. The latter, so this is the carbonylative style cross coupling. So, this is the vinyl aryl iodide, and this is the vinyl tin, and this carbonyl group is coming from the carbon monoxide, and you can see this is the reaction is happening. And the added carbonyl is later converted to a terminal alkene by Huttig reaction, allowing for the key tertiary nitrogen atom and the pentacyclic core to be formed by Ajakov-Manik reaction. So, this is the final product, but this reaction is very important because this is the carbonyl group is formed, where carbonyl group is attached to an aryl and a vinyl component. So, this intermediate is formed by style reaction, and this work was published in JACS 1993. Louis Hegda's 16-step racemic total synthesis of jatraphone involved a style carbonylative cross coupling as its final step to form the 11-membered macrocycle. In lieu of a halide, a vinyl triplet is used there as the coupling partner. So, this is important. This is intramolecular style coupling. Because your vinyl triplet and vinyl tin both are in the same compound, and now also they have particular geometry. You can see here, this is the trans, these two groups, and this also trans, and this carbon monoxide is used here, and with palladium catalyst DMF you get this ketone, and this geometry is intact. So, this is also trans and this also trans. So, geometry is important that it is retained and carbon monoxide is insert. So, ketone is formed. This is a very important reaction and was published in JACS 1990. Now, we will discuss another reaction, Stille-Kelly coupling reaction. So, in this reaction we will see that dibromide is converted into a cyclic product. So, using the seminal publication by Avon in 1976 which forms aryl sternes from aryl halides and distannine. So, this is important, distannine and aryl halide to generate aryl stannine, and Kelly applied this process to the intramolecular coupling of aryl halide. So, this is also intramolecular reaction. This tandem stannylation aryl halide coupling was used for the synthesis of a variety of dihydrophenanthrenes. So, this is the reaction, you can see two halides are there, generally X is equal to bromine, iodine, etc. And if you put this distannine and palladium ligand, etc., then you get this cyclization. So, intramolecular coupling, you can see this carbon and added to this carbon. So, intramolecular coupling. So, this reaction was reviewed in this book, Strategic Application of Name Reaction in Organic Synthesis, 2005. Now, we will see the mechanism. What is happening here? The palladium catalyst oxidatively adds to the most reactive CX bond like this, two most reactive one to form 14. So, this is the 14, that is the oxidative addition, followed by transmetallation with distannine. So, this is the important reaction, that transmetallation will happen and you get this X is displaced by this tin alkyl whole 3. So, earlier we have seen the tin alkyl whole 3 and vinyl which was group was transferred, but here SN alkyl whole 3 and SN alkyl whole 3 is used. So, what happened? This SN alkyl 3 is migrated to palladium. And now, the reductive elimination will happen from this one to generate 18. So, here what happened? The aryl tin component is generated. Now, this palladium will be generated again and this palladium will do the oxidative addition to generate this one 19. So, the regenerated palladium can oxidatively add to second CX bond of 18 to form 19. And followed by transmetallation, you get this transmetallation, you get this palladium comes to this, actually this is the Stille reaction is happening here, this is the Stille reaction, because you have the tin component and you have the oxidative palladium component. So, the Stille reaction happens and you get this intermediate followed by reductive elimination, you get this compound, this is the product, and catalysis is generated. This step is very important, that distannine is used and distannine is generating this tin component, aryl tin component, and then this is reacting with this aryl halide with palladium catalyst. Some examples, Zizek, Lee et al. Made use of this Stille coupling in their synthesis of a variety of benzo 4,5-fluoropyridines ring systems. They invoke a 3-step process involving a Backward-Hartwig amination followed by an intramolecular Stille-Kelly coupling. So, this is the reaction. So, first what happened, the Backward-Hartwig coupling happens here with palladium catalyst. So, this NH2 add to this aryl iodide bond and you get this amine. So, amination happens and then this Stille-Kelly coupling reaction, because you can see two aryl bromide is there. Now, distannine you have to add and these are the additives, this is the catalyst PDPPH3 whole to Cl2 and then you get this compound. So, here they are telling the aryl iodide bond will oxidatively add to the palladium faster than either of the aryl bromide bonds. So, this is selective amination is happening in the aryl iodide. So, two aryl bromide is formed now here, Stille-Kelly coupling will give this product. This was published in Organic Letters 2002. Now, we will discuss tributyl tin hydride. This is very popular reagent in radical chemistry. Tributyl tin hydride Bu3SNH is a useful reagent for the removal of halogen I and Br from alkyl halide by hydrogen. The reaction is performed in the presence of light or radical initiator AIBN. The mechanism involves formation of alkyl radical by abstraction of the halogen by Bu3SN dot. So, this is the reaction. Suppose example, this is the alkyl bromide AIBN. So, this is structure of AIBN. This is the radical initiator, this AIBN, radical initiator. Because it generates nitrogen and generates a radical. So, that is the here, this is the radical initiator, and around 70 degrees centigrade nitrogen will be eliminated as gas and this radical will formed. So, this radical is stabilized by cyano group also. And now, the initiation will happen, this radical generates the tributyl tin radical. So, this is very important, this radical generates the tributyl tin radical by this way, the hydrogen dot H dot is taken up by this radical. Now, Bu3SN dot will react this bromide to generate the alkyl radical. So, this is the alkyl radical and Bu3SN Br will be formed. So, this alkyl radical again will react with tributyl tin hydride. So, it will take a H dot from tributyl tin hydride and this will be regenerated. So, this is regenerated because this again will react with the substrate. So, these are the propagation. So, this method is very useful for dehydrohalogenation of aryl chlorides or bromides, iodides, etc. So, in the reactions of tributyl tin hydride, the alkyl radical generated from alkyl halide undergoes reaction with alkenes to give alkane via the formation of new carbon-carbon bond. Both inter and intramolecular version of the reactions extensively studied. An example for the tributyl tin mediated addition of nucleophile radical to electrophilic alkene. So, this is an alkyl iodide and we have seen that with tributyl tin hydride AIBN 5 mole % you get this radical. So, this is nucleophilic radical and this is an electrophilic alkene. So, this is acrylonitrile and one electron goes there and there. So, you get a radical here and this radical of course stabilized by cyano group and then this radical will react with tributyl tin hydride to generate the neutral compound, that is the product, and tributyl tin radical again will generate, so that the cycle will start again. Also, with tributyl tin hydride mediated addition of electrophilic radical to nucleophilic alkene also is possible, like this one. This is the diester and with tributyl tin hydride you can generate this electrophilic radical AIBN 5 mole %, you generate the electrophilic radical and now if you put an nucleophilic alkene. So, this is electron rich alkene, and here also electron goes like this. So, you get a radical here and that radical again will react to tributyl tin hydride like earlier, you get this product. Examples, here the radical which is formed is cyclizing actually. So, you can see this CH2I is generated this will be CH2, a radical here, and now this radical will migrate. So, this radical will add to this double bond, and that another radical will form, that will add to the triple bond. So, you get this tricycle compound. These are actually very important because many natural product this moiety is there. So, this is like hirsutene compound, this structure is present, and this was published in tetrahedron 1985. Also, if you have a beta keto ester, then again this will be CH2 and you generate a radical here. That radical will add to the carbonyl group to generate this one O dot, and this bond will break to generate this compound keto ester. So, keto ester. So, 1, 2, 3, 4, 5, 6 keto ester is formed. So, this is very important that the radical can do many reactions. This was published in JACS 1987. Now, we will discuss bismuth based reagents in organic synthesis, and here we will see bismuth +3 and +5 are the main oxidation states. So, first we will discuss preparation of organobismuth compounds, then preparation of organobismuth 5 compounds, organobismuth and bismuth reagents in organic synthesis, arylation reactions, cross coupling, aldol, epoxide opening, alkylation, arylation and carboarylation reaction, and hydroxocarbonylation reactions. So, first we will discuss general about organobismuth. So, organobismuth compounds are organometallic compounds containing a carbon to bismuth chemical bond. The main bismuth oxidation state are bismuth +3 and +5 as in all higher group 15 elements. And the energy of a bond to carbon in this group decreases in the order phosphorus higher than arsenic, then antimony, then bismuth, because bismuth is large in size. So, the bismuth carbon bond must be weak. Preparation of organobismuth compounds for first 3 compound. Organobismuth 3 compounds can be prepared from bismuth trichloride by substitution with the corresponding carbon nucleophiles, generally of the form of a Gigner reagent or alkyl aryl lithium species. Triaryl bismuth 3 compounds are typically crystalline solids that are not air and moisture sensitive and can easily be purified by recrystallization or chromatography, thus making them an attractive reagents for organic synthesis. So, they are not, bismuth 3 compounds are not moisture and air sensitive. So, they are very useful in that way, and with bismuth trichloride you can generate this trialkyl bismuth, trialkyl or aryl bismuth with appropriate Gigner reagent 3 equivalent. This was reviewed in Chemical Reviews 1989. Now, we will see the example of bismuth 3 compound synthesis. The Gagnon group has demonstrated that chemical modification of the substituents of the bismuth center can be achieved after formation of organobismuth 3 with aryl Gigner to form triaryl bismuth complexes. So, this you can see aryl bromide is present, and with this isopropyl magnesium chloride, this is converted to Gigner, aryl magnesium bromide. And then this, of course, 3 equivalent is present, then this will react with bismuth chloride to generate this triaryl bismuth. And now again you can do this Gigner at this ester with methyl magnesium bromide 6 equivalent, and you get this tertiary alcohol in 84% yield. This was published in JOC 2016. Now, we will discuss preparation of organobismuth 5 compounds. So far we have seen bismuth 3. Now, 5 complexes may be accessed directly from organobismuth 3 through oxidative addition to a halogen and thus displacement of the newly formed bismuth halogen bond for a bismuth carbon bond with an alkyl or aryl lithium or Gigner reagent. So, this is the reaction. So, whatever you have generated the trialkyl bismuth or triaryl bismuth, that you have to react again with chlorine or SOCl2 to generate this one R3BiCl2. Then further Gigner reagent Rm or R dash M, then you can get R5 bismuth. So, here bismuth in 5 oxidation state. Now, we will discuss some examples of the reactions organobismuth reagents. So, this is the bismuth Ar3Cl2. So, this is in bismuth in 5 oxidation state. So, this is triaryl dichloride bismuth is one of the well known triaryl bismuth 5 reagents capable of effecting many arylation reactions. Regiospecific alpha arylation of enones and enols by using BiAr3Cl2 reagents under nucleophilic catalysis conditions. So, this is very important, alpha arylation of enones and enols. The use of tributyl phosphine was a complement to the related palladium catalyzed methods for enolate arylation. So, this is the reaction, this is cyclohexenone. So, this is an enone, and if you put tributyl phosphine 20 mole percent, Ar3BiCl2 100 mole percent, because one aryl group will come from this reagent, and this is unique base, you need one equivalent, and this is the solvent 25 degrees centigrade, then you get this product. So, this is very useful reaction. Arylation happens selectively at the alpha position. So, alpha arylation of enones, alpha arylation of enones. It is a very useful reaction, and this was published by Chris J, a well known organic chemist from USA, in JACS 2004. So, what will be the mechanism? So, this is the reaction, again we have drawn here the tributyl phosphine, and this is the BiAr3Cl2. So, what could be the mechanism? So, first we know the phosphine is a nucleophile. So, this is nucleophilic catalyst, the tributyl phosphine, that adds to the beta position and to generate this enolate, and then the enolate reacts with this reagent. So, enolate reacts with this and one Cl minus will displace. So, 2 chlorine was there, now it is 1 chlorine, bismuth still in 5, because bismuth connected with 5 component, and now the reductive elimination will happen. So, this is important, reductive elimination will happen, and the reductive elimination is happening in such a way that the aryl group is migrated to here. So, here this is the byproduct, that is the bismuth species. So, here bismuth in 3, because it is connected to 3 component, and you regenerate tributyl phosphine, also HCl is generated. So, this is the mechanism, that first the tributyl phosphine adds to the beta position, generate the enolate, then enolate reacts with this, and this enolate is converted to the ketone with the aryl migration. Now, we will see the cross coupling reaction. Organobismuth reagents can also be in cross coupling reaction like tin component. Organobismuth compounds such as triaryl bismuth reagents are referred to as an atom efficient organometallic coupling partners for CC bond formation. The reason was that triaryl bismuth reagents could react with more than one equivalent of electrophilic coupling reagents. This is very important, and this the proposed cycle, that the cycle A. So, this is the cycle A, this is A. So, this is the addition first is happening in cycle A. Palladium adds to RBI, because this is very weak. We have already told that boron carbon bond is weak. that is the explanation here. The cycle A occurs because of the weak bismuth carbon bond, and it was inefficient to readily add to palladium 0 species to generate this. Now, other partner will come, suppose R dash O triplet, the bismuth O triplet will be generated and you get this. Now, palladium is connected to both R and R dash, and of course, the reductive elimination will happen. Reductive elimination to generate the palladium 0, and this is the product. Now, another cycle is possible also, that R dash O triplet adds to palladium first to generate this, and now the transmetallation will happen. R bismuth goes to bismuth triplet and this R group goes to the palladium to generate this same intermediate R palladium R dash, and after reductive elimination you get this. So, this was published in Organic Letters 1999. Now, the aldol reaction we will see, and first one is vinylogous Mukaima aldol reaction. So, bismuth triplet here. Bismuth triplet is a Lewis acid. Lewis acid. So, bismuth triplet is Lewis acid and it can react with this furan OTMS, and this is the vinylogous Mukaima aldol. So, what will happen? It will add here and you get this lactone motif here and the double bond generated here, and you get this product. This is 2 chiral centers are present, sin anti-94:6. So, sin is major here. And in 91% yield, so this is very efficient and only 1 mole % of this bismuth triplet. Now, this reaction can be also possible with chiral ligand, and you can develop an asymmetric version that is presented here with aqueous formaldehyde, and this is the enol silane with this ligand. This is C2 symmetric ligand, and with bismuth triplet again with 1 mole %. So, 3 mole % ligand and 1 mole % bismuth triplet. So, you have to make sure that bismuth binding with this ligand and becoming a chiral bismuth, and this is another ligand bipyridine. With this solvent you get this product. It is 91% EE and 93% yield. So, this is where the reaction is happening, this add to the formaldehyde. So, this was published in Organic Letters 2005. Also, Michael reaction is also possible. Mukaima Michael addition reaction like this. This is disilane is there, and with this bismuth triplet here 20 mole % dichloromethanes solvent followed by TFA addition, you get this 5-member ring with a cyclopropane. So, what could be the mechanism of this reaction? And first thing is the Michael reaction is happening. So, this is the reaction again has been drawn. So, what happens, this adds to this. So, this is first step is Mukaima Michael is happening here. It is added to the double bond, and this double bond is migrated to here, and again in presence of acid this double bond isomerized. So, here this is isomerization is happening, isomerization, and then this nitrogen is reacting to the carbonyl group to generate this hemiaminal. Hemiaminal is generated, and that again rearranges, generate the ketone, and this carbon attacks to this. So, the cyclopropane is generated, and this is only possible with TFA. So, that this OTMS will be a living group. So, this is an useful method with bismuth triplet, that Mukaima Michael reaction followed by rearrangement cyclization, you get this 5-member ring. Now, epoxide opening reactions we will discuss. Organobismuth catalyzed epoxide opening reaction is possible, like cyclohexane epoxide with aniline, and catalyst B, that is the bismuth reagent. Here you can see aryl groups are attached also with sulfur, and with this catalyst, actually this is catalyst 5 mole % only used, and water solvent 20 degree centigrade, you get this beta amino alcohol. Beta amino alcohol, these are useful products. So, this is the trans geometry, you get 91% yield. This was published in Tetradan later. The reaction can also be possible in the asymmetric fashion, and if you use the chiral ligand, like earlier we have used this ligand, the same ligand. So, this is C2 symmetric, the same ligand can be used for the epoxide opening reaction with aniline, and here this is the cis epoxide, this cis epoxide, and you get this product, the beta amino alcohol is formed in 80% yield with 88% enantiomeric excess, and SDBS, this is the structure of SDBS, this is surfactant which has been added in the reaction, and this work was published in Heterocycles 2005. Now, we will discuss alkylation reaction. So, if you see the structure here, an aldehyde O silyl group and allyl silane you have to add with bismuth bromide 5 to 10 mole %, and you get this tetrahydropyran product in trans is to cis 99:1. So, this is very selective reaction. So, what is happening? BiBr3 in H2O, it generates a small amount of acid. So, this is very important, small amount of acid is generated, and that acid will activate the aldehyde, of course, and then the addition will happen, you get this intermediate, then R3SIX will eliminate, and you get this lactol. So, this lactol is formed, and lactol, we know that lactol in presence of acid generates the oxonium ion, and once the oxonium ion is generated, then the allyl nucleophile will react, allyl silane will react to generate an allylation. Now, this product will be selective, that the trans product will be formed exclusively, and this R3SiOH regenerate this and regenerate HX. So, this is the catalytic cycle, and this work was published in JACS 2003. Now, we will see another reaction, enantioselective allylation reaction. This was an allylation reaction, instead of allyl silane here allyl tene is used, allyl tributyl tene, because allyl tributyl tene has a allyl nucleophile here, and if you use naphthaldehyde, then this allyl alcohol is formed, 84% yield, 92% EE. So, this reaction is very useful, and the ligand is used, this is the Trost ligand, and bismuth triplet is the catalyst here. So, ligand you have to use 15 mole %, bismuth triplet 5 mole %, also you need honic base 50 mole % and molecular sieve, so that the reaction will give high yield and high enantioselectivity. This was published in Chemistry European Journal 2012. Now, we will discuss arylation and carboarylation reaction. So, if you use mesitylene with acid chloride with bismuth chloride 10 mole %, 120 degree centigrade, this of course you have to use excess, and you get this olefin. This is very interesting reaction, olefin is formed here, with this group is coming from this also, of course. So, what could be the mechanism of this reaction? The first, this Friedel cup acylation will happen, Friedel cup acylation to generate this ketone, and this ketone will be in the enol form, and this enol will go to the vinyl chloride. So, this is very important, vinyl chloride is formed here, Cl minus will displace OH minus, and again the acid mediated vinylic substitution. So, this is vinylic substitution reaction is happening. Vinyl substitution, that aryl group displaces the chlorine and you get the olefin. So, this is a reaction. First the phenyl cup acylation to generate a ketone, then the enolization, then the Cl minus will displace OH minus, and then the vinylic substitution will generate the olefin. So, this is the catalyst bismuth trichloride. Of course, this reaction is high temperature 120 degree centigrade you have to do. This work was published in Advanced Synthesis Catalysis 2006. And lastly, we discuss hydrocarbonylation reaction. So, this is the reaction, there is a acid motif is there and alkyne is there, internal alkyne with aryl substituent, bismuth triplet 2.5 mole %, you get this 6 member ring and 5 member ring, this 6 member lactone and 5 member lactone, and Ar is equal to pH, you get 72:28, and Ar is equal to 4-methoxyphenyl, that case 20 degree centigrade you get less yield, but better selectivity, 100% this product is formed. So, when Ar is equal to 4-methoxy, because that is electron donating. So, we will see the mechanism. Here this can be also A star, because here this is be A star is used in the mechanism. So, this carbonyl group of the ester or acid will coordinate with bismuth along with the triple bond, and the addition will happen because the triple bond is activated, then this carbonyl group will add to the triple bond, and this is the endo addition, this is 6 endo addition and this is 5 exo addition. These are dig, 5 endo dig, 6 exo dig, because it is adding to triple bond, and after that this will be carbonyl group, and this R1 R2 can migrate to here in the bismuth position, but since we are using acid here, so this is hydrogen, so hydrogen comes here and you get this product. So, this is hydrogen here, you get these products. So, this is an interesting reaction that with bismuth triplet, if you have a carboxylic acid and alkyne, then you can get the cyclization and you can get lactone. So, these are lactones. Okay, so this is the published in Organic Letters 2008. So, today we have discussed first organotin reagents, and first we have discussed tetraorganotins, then tri, di and monoorganotins. So, in tetraorganotins we have seen they can be generated by Gigner reagents, and tri, di and monoorganotins can be also be generated by Gigner reagents when you have used R2 tin Cl2 like this. Also by Hartz method also you can generate this tetraalkyl tin, that is the alkyl chloride sodium, and you have to use the tin reagent. So, then you can get this tetraaryl tin or tetraalkyl tin. Also aluminum reagent can also be used to generate this. Then organotin halides we have seen, and organotin hydrides we have seen the preparation, that with lithium aluminum hydride you can prepare this reagent, the organotin reagents, and tributyl tin hydride you can generate. Reactions of organotins, Stille reactions we have seen. The Stille reaction is a powerful coupling reaction where the tin component is added to the vinyl triplet or vinyl chloride, vinyl iodide or bromide, and you can get this cross coupling product. And Stille variant also is there, Stille Kelly coupling, where the intramolecular dihalo component are coupled to give this product, cyclized product. And carbonylated Stille coupling also is an useful reaction where carbon monoxide is used, and this reaction can also be used in natural product synthesis. Reaction of tributyl tin hydride also we have seen, this is the with AIBN it generates the radical, and this radical as can add to the alkyl bromide to for the dehydrohalogenation. Also it can add cyclize, it can add to olefin, then the radical migrate to the triple bond, that also process, and we have seen a 3 cycle is generated in a single operation. And lastly we have seen the bismuth. So, organobismuth we have seen first the bismuth 3 compound, then bismuth 5 compound, and their reactions we have seen, arylation reaction we have seen. The enone, when it is treated with this Ar3BiCl2, the alpha arylation of enone is forming. This reaction is very efficient, and also cross coupling reaction we have seen, because the bismuth carbon bond is very weak, so it can be useful for the coupling reaction, and less than 1 equivalent can be used. Also, you have seen the Mukayama aldol reaction that can be performed in asymmetrically also with chiral C2 symmetric ligand. Then epoxide opening reaction we have seen with aniline, and alkylation reaction we have seen, and we have seen arylation and carboarylation reaction also we have seen, that when the tetrahydropyran can be generated. And lastly, we have seen hydroxycarbonylation reaction, where an acid and alkyne motif is there, and the acid is adding to the triple bond, and you generate the 5 membered or 6 membered lactone. Thank you.